Hi, welcome back to our web-based workshop, Math as a Second Language, where today we're going to talk about the arithmetic of quantities. Remember, in our opening lesson, we talked about the idea that we talk about numbers, but what we see are quantities. Unfortunately, all of the tables and things that we learn in mathematics are always in terms of the adjectives. Now, I won't always be able to think of an appropriate anecdote to open a lecture with, but every so often one pops into mind that fits very nicely. And they tell the story of the chef who used to make lamb stew, rabbit stew, doesn't matter, whatever. I think rabbit stew is better. And they said to him one day, "Do you use any additives?" He says, "Well, I use a little horse meat." And they said, "How much?" He said, 50-50, one rabbit, one horse. Now, the point is that the adjective one always means the same thing, but the quantity one horse is not the same as the quantity one rabbit. So, for example, when you study math, just talking about the adjectives, you'll see things like 1 equals 1, but 1 inch is not equal to 1 foot. You see, the adjective one is always equal to the adjective one, just like the color blue is always the color blue, but the quantity 1 inch is not the same as 1 foot. On the other hand, 12 is not equal to 1, but 12 inches does equal 1 foot. So again, what happens is, because when you're using the words, you can distinguish between 1 inch and 1 foot. Obviously, they're different quantities. When the nouns are missing, it can be confusing. If all you see is the 1, how are you going to tell whether it modifies 1 inch or whether it modifies 1 foot? So the first rule in dealing with quantities, and this is going to sound very mathematical. All I really did here is replace m and n by 1. But if this is just something we do in math. In other words, so if you don't get the idea that we're just thinking of a particular pair of numbers, we let m and n be any numbers. And when we write, what we're saying is, if m and n are numbers, and we write m equals n, we're assuming that m and n are modifying the same unit, that is the same noun. Like as we just said, 1 is equal to 1, but 1 inch is not equal to 1 foot. Okay, so are we okay on that? In other words, when we write down two numbers are equal, we're talking about the adjectives, meaning as adjectives they're equal, but in terms of quantities, when we're thinking of quantities, the adjectives can be the same, but the quantities can be different. Well, here's an interesting one. Let's suppose that you tended to be a bit math-phobic. And I was going to be teaching you a workshop now. And I come into the room, and the first thing I write down is 3 plus 2 equals 40. At that point, there are two possible reactions you could have. The first one is, wow, he's so brilliant, this is amazing. And the other one is, thank God he may be one of us. We look at this, and this seems insane. We don't have any place that tells us this. On the other hand, look what happens as quantities. 3 dimes plus 2 nickels equals 40 cents. Okay? In other words, 3 plus 2 equals 5 is assuming that 3, 2, and 5 are adjectives modifying the same noun. In other words, in the arithmetic of quantities, when we write 3 plus 2 equals 5, we are assuming that 3, 2, and 5 are modifying the same noun. Now, at this point, you may say, well, that's nice that he's doing that, but what good is it? Well, let me just try to give you a few examples. If I know that 3 plus 2 is 5 whenever 3, 2, and 5 modify the same noun, how much is 3 billion plus 2 billion? Well, the nouns are the same, so we keep the common noun and we add. Pretty easy. Now, look what happens when we write this in the language of place value. The 3 is modifying billions, so that means we have 3 billions, no millions, no thousands, and no units. Now, if I teach a first grader who can read, my rule that you can only add when they modify the same noun, can you visualize that even though the youngster doesn't know what the word billion means, he knows that 3 of them and 2 of them are 5 of them? Compare this with this. Can you visualize that looking at this is somehow more scary than looking at this? In other words, he says, I'm a little kid, I can't keep track of all those numbers. So again, this makes a very nice transition. In other words, the 9 zeros are place values way of translating the word billion. Now, just in the same way that a youngster might not know what the word billion means, suppose I say to a student, how much is 3 glugs plus 2 glugs? Student says, I don't know what a glug is. I say, I don't know either, but 3 of them and 2 of them had better be 5 of them, because 3 and 2 are modifying the same noun. You say, well, where does that ever come up? I have taught algebra classes where I ask students to simplify this, and they say, but I don't know what x is. It doesn't matter. 3 of them plus 2 more of them are 5 of them. Of course, the value of 3x plus 2x depends on what the value of x is. In other words, this will have different numerical values for different values of x, but the point is that 3x plus 2x is 5x. 3 of anything plus 2 of the same thing is 5 of the same thing. How about this one? 3 sevenths plus 2 sevenths. Well, you say, I don't know what a seventh is, but I can only add if they modify the same noun. So 3 sevenths plus 2 sevenths is 5 sevenths. Well, that's kind of easy, wasn't it? Look what happens when we write this in the language of fractions. The 3 becomes the numerator. See, enumerate to count. To count answers the question of how many. How many is an adjective. See, the numerator is an adjective. People will say numerator means top. Well, if numerator means top, just use the word top, because everybody knows what that is. See, the numerator enumerates, it's the adjective. Denominator sounds like denomination, the size. 3 of what it takes 7 of to make the whole thing. So 3 sevenths looks like this. 2 sevenths looks like this. How many students look at this and say, oh, I'll add the 3 and the 2 and the 7 and the 7? And they put down 5/14, even though if they understood the language, they would know that the answer is 5 sevenths. You see, you wouldn't say, let me make up a funny example here. How much is 1 nickel plus 1 nickel? Well, you say, okay, the nouns are the same, it must be 2 nickels. What about the kid who says, oh, 1 and 1 is 2, and a nickel is a dime? You can add this way, but it don't give you the right answer. See, if I say to a student, you can't add that way, he says, I just did. Yeah, you did, but you got the wrong answer. So look at how much we can do just with the simple rule that when we don't see the adjectives, any equality assumes that the adjectives are modifying the same noun. And now we come to the third and final rule that we need. We all know that 3 tens plus 2 tens is 5 tens. Ask a student, how much is 3 tens times 2 tens? And there's a very good chance that what they'll say is, oh, the 3 times 2 is 6. And they'll say 6 tenths. Well, the funny part is that's wrong. Why? How do we know it's wrong? Well, 3 tens is 30, and 2 tens are 20. And when you multiply 30 times 20, you get 600, not 60. And this leads to a very strange rule. It sounds strange, but it really isn't. When you multiply 2 quantities, you multiply the 2 adjectives, the 3 and the 2, in this case would give me 6. And here's the tricky part. You also multiply the 2 nouns. And the way you multiply 2 nouns is you write them side by side. Looks funny. 6 10 tens, see? Now what's 10 tens? It's 100. In other words, if you multiply the adjectives and multiply the nouns, you get the correct answer. In other words, the rule would be stated as, if A and B represent any units, 3 A's times 2 B's would be 6 AB's, whatever that happens to be. And we have examples of that in real life. As adjectives, 3 times 2 will always be 6. Doesn't matter. Always going to be 6. 3 kilowatts times 210 is 6 something. 3 pounds times $2 per pound is 6 something. 3 feet times 2 feet is 6 something. Here's a strange one that we don't usually see. 3 inches times 2 feet, that's still going to be 6 something. And let's see what we get here. We also have to multiply the adjectives. And maybe you've seen this on your electric bill. The 3 times 2 gives you 6, and the kilowatts times hours give you kilowatt hours. Still the 6 here. 3 pounds times $2 per pound, that would be 6 pounds, dollars per pound. That sounds like a very complicated thing. But if you know the price per pound and a number of pounds, you multiply them together, the answer will just be $6. And what's 3 feet times 2 feet? 3 times 2 gives me 6. Feet times feet gives me feet, which we often call what? Square feet. Okay, and we sometimes write it this way mathematically. Here's a strange one that most people think. See, in other words, when you're finding an area, you always multiply the length by the width. So the 3 times 2 will always give you 6. What happens over here? The label would be inch feet. And the person might say, I never heard of inch feet. No, it's a new measuring unit. It's 1 inch by 1 foot. Like if you buy 3 yards of material, it's not a linear measure. The 3 yards is actually so many yards. It comes at a certain width. So it might be 3 yards by 1 yard or something like that. But we're just not used to talking about inch feet, but it makes perfect sense. And we can talk more about that later. Now, how does this come up in the school curriculum? Well, let's just apply what we just did. 300 times 2,000, what should that be? We multiply the 2 adjectives. 3 times 2 gives you 6. 100 times 1,000 gives you 100 thousands. Okay? Now, look what happens when we write this in place value. 300 looks like this, and 2,000 looks like this. And what was the mechanical way that we learned to multiply here? Ignore the zeros, multiply as if the zeros weren't there. Well, there's your 3 times 2. Then count the number of zeros, 1, 2, 3, 4, 5, and that's how many, oh, I didn't mean to write that. That should be a 6. Count the number of zeros, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And what's the answer? 600,000. So you see that those 3 rules will permeate our entire course. You'll get more familiar with them as we use them. But I just wanted you to see this for a start. And you can actually do this in the classroom just to have the kids practice their tables. Studying the tables can be very boring, but if you make sort of a challenge out of it, something that the kid says, wow, I never realized that, the kids will then do the drill because they're interested in seeing what the answer is. So for example, let's look at 3 2s times 2 4s. According to what we just said, the 3 times 2 would give you 6, and the noun would be 2 4s. And how much is 2 4s? It's 8. And so the answer should be 48. Now do it the way you learn in the tables. 3 times 2 is 6. 2 times 4 is 8. And from the tables you get 6 times 8 is 48. Again, the kid is now drilling, but he's interested in seeing, does this really give you the same answer that this does? And if it's a more advanced elementary school grade, you can put in more than 1 digit. 3 times 2 would still be 6 here. 5, see 3 5s times 2 6s. It would be 6 5 6s. Looks funny, but 5 6s is 30. And 6 times 30 is 180. And what happens over here? 3 5s would be 15, and 2 6s would be 12. And if you multiply 12 by 15, When I went to school, we learned the tables through 12. 12 times 5 is 60, put down the 0, carry the 6. 12 times 1 is 12, plus 6 is 18. Same answer, still doing the drill, but now they're having more fun with it. And that about brings us to where I want to be today. And what I want to do from here on in is to end each lesson with what I call a practice question, practice problem. What I'm going to do is I'm going to put a problem up, and you keep looking at it. In other words, pause the video till you're sure that you've read the question. And then after you've answered the question, resume watching, and I'll go through the solution with you. So the practice problem is this. Using the fact that 40 is 5 times 8, see if you can fill in the blanks to correctly solve the problem below. 3 times some quantity times 2 times another quantity is 40 times a third. What numbers can we put in here to make this a true statement? Okay? And when you've looked at this long enough, and it's not important whether you can do the problem or not, come back and then I will show you how I interpret the problem and what I get out of it, okay? Okay, so freeze this. Okay, I'm now going to go on with the lecture. And so the problem was, what can we put in here to make this a true statement? Well, notice I gave you the hint that 40 is 5 times 8. We want these adjectives to be the same, modifying the same amount. What numbers do we have here that we don't have over here? We have a 3 and a 2. So I'm going to have to multiply by 3 times 2 over here. Okay, now what's over here that I don't have over here? A 5 and an 8. So let's see what that would say. It's 3 5s times 2 8s equals 40 6s. And by the way, you could break this down differently. You could put the 8 over here and the 5 over here, whatever. Let's see, 3 5s is 15, 2 8s is 16, and 46s is 240. It's 40 times 6. And let's see how this works out. Okay, this is how all of our lessons are going to run. We will basically go through something. I will end by giving you a problem to think about, give you a chance to internalize what we're talking about, go on. And remember, you can pause, rewind, fast forward, whatever you wish to do. And I'm going to look forward to seeing you next time.